There we go. Steve Mack, I'm with Turck. We're here today to talk about distributed I/O and cost reductions with using distributed I/O. So this is going to be more of a discussion about concepts than it is specific product solutions, although we do cross that line back and forth a few times. So we'll start out talking a little bit today about what is a traditional control system, how those kind of merge over into distributed I/O control systems, and some of the Turck technologies for cost reduction. While I'm going to kind of present the Turck technologies, these are really, not necessarily completely Turck specific. There are other vendors that have competing products to everything that we'll look at today. So what do we mean when we talk about a traditional control system? We're typically talking about a main control panel with the majority of the I/O wired directly back to the terminals in the main panel. So we're talking about a very large panel like the one pictured here, with possibly multiple racks of I/O and a lot of terminals. This could actually be considered a small main panel for a very large process system. Typically, all of the I/O in this panel will be either on the PLC rack, or it will be remote racks of the PLC brand. So if you're using a Rockwell PLC here, this would be a Rockwell PLC I/O rack, and there could be 3 or 4 I/O racks there. There is kind of a hybrid mixed solution here where we will have this main panel, and we will also have remote panels. And in the true traditional legacy control system, even though we have remote junction panels, those are really just kind of localized wiring points. All of those wires are directly wired back to the main panel. So we're not using networks across the production area. Then we have what I would call transitional control systems. So this is going to make use of a main panel as well. But we're going to have remote panels. They can vary in size and vary in type. If we look, I'll start on the right-hand side here. This is a fairly large enclosure with a modular I/O rack that is going to have a network connection. And we have a lot of terminals in here. So we're still wiring things direct to terminals, and we're probably making conduit entries into this panel. The middle picture is a little bit smaller of a remote panel. Again, we have a modular I/O system with a network connection, and all of the wires coming in come to terminals. In this case, we're using quick connect terminals. On the left side, we have an even smaller panel, this with an IP20 block that is networked. So we're coming in here through strain release, just bringing in cord. And in each of these cases, the reason I call these kind of transitional systems is that we still have remote junction boxes. We have these remote control panels, but instead of wiring all of the I/O signals back discretely, we're taking those back on a control network. So that leads us to true distributed control panel, where we're trying to have a smaller main panel, and we're trying to get the I/O to remote blocks. So what that looks like, potentially, is, here's an example of a process skid where, we've obviously got a very small control panel here, and we have network cables coming out to I/O blocks. And we've got a few I/O blocks. Even though it's not a very large skid, we're able to save money and time in putting the skid together by having a smaller control panel and having the I/O blocks closer to the I/O point of use. Even though it's not a long distance of wiring from here back to the main panel, if we save that, it saves time, and time is always money. And one thing to keep in mind is that we do have these remote blocks available for Class 1 Div 2 locations. So that seems to always be the first thought that people have is if I'm in a hazardous location, I need to have an enclosure. That's not always the case. We do have blocks that are Class 1 Div 2 rated. It does require the use of a lock-fast clamp on the connection point here at the block so that it requires tool removal and cannot be removed without removing power. On more of the machine side, we have the ability to do discrete I/O on a machine with multiple blocks and multiple combinations of blocks and modular systems. So the idea being here that each of these sections of a machine can be built up independently. They can be broken down for shipping. And the only connection we have between these blocks are these two signals here. So one of these is network and one of these is power. We have, I should say the industry has blocks available that give us all combination of analogs, digitals, serial ports, RFID, encoder inputs, pretty much anything that could be needed as an I/O point is available in an IP67 block, including safety. So that makes this, truly a modular solution. And this can be taken to the extreme where we have a customer who builds a machine, not like this, but the same concept. And each of the 7 sections, there's 7 pieces that make up their machine, is built in a separate facility. They don't come together to be tested until they get to the customer's facility. So you can literally take this idea of distributed I/O to that level of an extreme where every section of a machine is built and put together independently. It all meets up at the customer's final installation location, but it can all be tested before it ships, because each of these sections has a function, and that function can be tested. You will note that we have some IP20 I/O in the mix here, because there are always some things that we cannot get in IP67. And typically on a machine, those items are things like servo drives and robotic controllers. And we do have cables rated for whatever environment we're installed in, right up through process and hazardous locations that we don't require conduit. So that helps us to save money also. So I am going to kind of review here some Turck products as to how we would solve some of these problems. But again, everybody has products like this. So it's really just showing more of the concepts of how things can get solved. We have modular in-cabinet solutions. This is our BL20 product line. The module on the left is our communications gateway. So this can be swapped out for multiple different protocols. And then the I/O is just stacked on to meet the needs. We have our FEN20. So this is a in-cabinet block solution. There are other versions of this for DeviceNet So we do have some different protocols available here. The bottom is our XCOM product line. This is very much geared towards the process industry. It is Class 1 Div 2 rated, and it is Zone 1 and Zone 2 rated, meaning that if you install this in a Class 1 Div 2 area, you can wire out to I/O points in a Class 1 Div 1 area without going through a barrier. The barrier is included in the I/O portion of this I/O system. It has the ability to use redundant power supplies and the ability to have redundant communications interface. So that makes it part of what is called high data availability systems. So very much oriented for the process industry, DCS systems, things like that. On the IP67 side of things, for machine mount, we have our modular product called BL67. Again, we start with a communications gateway on the left, and then we add modules as we go to the right. We have our IP67 block products. One on the left is our BL Compact. The one on the right is a TBN-L. We also have TBN-S, which is a miniature version of that. As far as Class 1 Div 2, we have that for the Ethernet version of the BL Compact, have it for the TBEN-L and the BL20. So I do want to just kind of dive into the TBN-L product a little bit to give you an idea of why block I/O works in so many applications. So our TBN-L block is, if we have discrete I/O points, it is 16 discrete I/O points. We have up to 2 amps per output. And here we have an important factor, -40 to +70 degrees C operating range. So if you've got a cold environment, and more importantly, a temperature changing environment where you're very prone to condensation inside of a cabinet, these blocks are fully potted. So there is no place for condensation to form inside. So they are very robust when it comes to temperature, vibration, shock, anything like that. These will actually hold up better than I/O inside of a cabinet. They are IP69K when used with the correct connectivity. We have fixed or configurable I/O points. So our digital points can be used as an input or an output. Galvanic isolation between the 2 incoming power supplies. So typically our blocks, V1 controls the communications gateway, V2 controls the output power. We support quick connect, device level ring topology, and ACD is how we add into the Rockwell PLC. As far as advanced features, we will be talking about this a little more: multi-protocol Ethernet, beep, FLC, and DPM. When we look at the TBN-S, this is, I don't know if these are exactly to scale pictures, but these are quite a bit smaller. You know, this is an M12 connector and this is an M12 connector. So you can see that these are much smaller in size. There are 8 discrete I/O points. This is literally the size of a stick of butter, just to give you an idea. And all of the features we talked about on the TBN-L are basically the same on the TBEN-S, except for the output power. We only drive a 1/2 amp of output power per point, basically because we're limited as to how much incoming power we can get on the M8 incoming power connection. So what can we do with these blocks as far as I/O connections? So we can do 16 inputs, 16 outputs, are 16 configurable, and there's no real configuration to it. You wire it as an input, read the input table, it's an input. Wire is an output, right to the output table, it's an output. And we have half in, half out block. For PLCs inputs or configurations, we can do EDS in anything on Ethernet IP. Anything on Profinet, we'll use a GSDML file. And then we have catalog files, which are specific to Rockwell. And those allow us full access to all of the configuration inside of our device. You'll see we've referred to these as LX. So L4 is 4-pin auxiliary power, L5 is 5-pin. All of the other features are the same. We do have some complex I/O available in the TBNL. We have a 4 RFID block. We have a 4 RFID block that runs codesys. So you can do your RFID logic locally in the block and just pass data back to your PLC. We have the EN1, which is a spanner block. And the spanner is very unique because it allows two PLCs that are on two different Ethernet networks to communicate to each other. So we do that by setting up input and output tables. So PLC A, it writes to the spanner into a data table. PLC B reads that data table. PLC B writes to a different table. PLC A reads from that second table. So the two are able to communicate data up to 480 bytes without either PLC being forced to do that protocol transition in the PLC. We have some background noise here. If everybody could just check that their phones are muted, that would help us quite a bit. So we also have our TBN 8 IOL block. So this is 8 IO-Link masters, and we will talk about that a little more. We also have Ethernet switches. So this is a big help when we start putting these distributed control systems out, and we often run out of the ability to have Ethernet continue to daisy chain through devices. All of our devices have a built-in switch, not everything does. Now we can put an Ethernet switch out in the field, and Ethernet is 100 meters length per run, so every time we put a switch in, we gain 100 meters. So if we have a large factory floor, spread out process system, we can spread these switches out and make the network go everywhere it needs to go. We also have a unique product here in that in the same TBNL housing, we can embed a codesys PLC. So this is now a master and a slave on our Ethernet protocols. It also has CAN open, and it has a few discrete IO points and some serial ports on it. So it's a very powerful little block. So if you've got a machine that is very small, very standalone, and you just want to have it be locally controlled and it doesn't even need a controlling enclosure, something like a block like that kind of takes this idea of distributed control right to the very end. So our TBN-S blocks have a little bit more, few flavors more in the discrete IO. And then we have a serial module, a 4 IO-Link module, and an RFID block. Again, these have our multi-protocol Ethernet. All of the same PLC interface features. And because these are smaller, we often find people stacking them into tight areas. So we've actually come up with a little clip, two versions of this, one that mounts to a steel plate, another that clips to DIN rail, and then the blocks clip into those. So we do have a way to organize these very well. As far as our analog inputs, we have a 4 analog input block. This is unique because it has current, voltage, RTD, and thermocouple, all individually selectable by port and all selectable by software. So you buy one module and use it for whatever analog you need. Our analog output is similar. It is current or voltage, and it is software selectable by each discrete port. Our digital inputs are available as M8 or the M12s. The specialty modules and the analog I/O modules are all available only as the M12 connections. So multi-protocol Ethernet is a unique concept for control systems in that we only have to have one block or one block type, regardless of the PLC that is being used to control the system. And our blocks will talk multiple protocols simultaneously. So we actually have customers where two machines are meeting, say it's a conveyor system, and the two PLCs will read the sensors at the exit of the upstream and entrance of the downstream machine so that the PLCs don't actually have to communicate together. They're just reading those sensors. When there's a box upstream, there's no box downstream, both PLCs can turn their conveyor on and pass that box down. It really simplifies some of the interface between machines. The three protocols that we support are Ethernet IP, Modbus TCP, and Profinet. They do make up the majority of the Ethernet, industrial Ethernet market right now. And because of our built-in Ethernet switch, you notice we have two RJ45s on our IP67 blocks. We have two M12 connections. We are able to support multiple topologies. So star topology is pretty much always supported because there is no need for a switch on the block. Line topology, we support with our switch. And again, every time we put a node in, we have this built-in Ethernet switch, we gain another 100-meter run to the next node. So that is what allows these systems to spread out over very long distances. And along those lines, if you have really long distances, I've done pumping stations that were 7 miles away. You can run fiber or you can do an Ethernet radio. Either one of those is suitable to be that link between nodes. We also support what is known as device level ring DLR topology. We are a certified slave for both Rockwell and Siemens. That is really the key, is the master that you need to run that. So some of the specific technologies that we use. So Beep is our backplane Ethernet extension protocol. And what Beep does is allows us to have one block that talks to the PLC. And then on the other side, there are multiple blocks that are communicating with the master block. So it looks a little bit like this. So we come into Ethernet port 1 on our master. We go out Ethernet port 2, in port 1 on our first slave, out port 2, and so on. And we can do this. There can be up to 32 slaves. So what happens is our Beep master now gets a very large I/O table, up to 480 bytes. That's the maximum size on an Ethernet IP device. And the whole reason for this is that the PLC makes one SIP connection or one Profinet connection to a block, and there's up to 32 blocks, or actually 33 blocks worth of data included in that. So for somebody who's buying a smaller PLC with a limited number of SIP connections, where in the past they would have been limited by the number of blocks that they could put out there, we now expand that number of blocks. So the requirements for Beep is that it has to be a linear topology. We cannot go through an Ethernet switch to do this. And there can be no foreign devices in the middle. So if we've got 2 slaves, and then we've got something else. And this could be a VFD, it could be a solenoid manifold, pretty much anything, even just an Ethernet switch. Then that breaks our first beep network, and we can start with another beep network on the other side. So beep is configured in the webmaster of the block, or I should say the web server of the master. Basically, you go into the web server page, you enable the master, you tell it to search the network. As long as it finds the number of nodes that you expected, you just click on accept, and you now have a beep network. And then the web server page will show you the detailed IO mapping for every block in there, so you know how to map it in your PLC. Cycle time is always a discussion when we talk about beep, and the cycle time is really not too bad here. So if we have a master with 1 slave, we're looking at 5 milliseconds for the master to get updated data from that slave. If we scale all the way out to 32 nodes, 32 slave nodes, we're going to be looking at 9 milliseconds to update the master with the data from all 32 nodes. So it is something that needs to be looked at. If you've got a high-speed application, this could be a concern. But we have a lot of applications where the network update rate that the PLC is scanning is far higher than just 9 milliseconds. So to summarize beep, we're looking at the consolidation of IP addressing. So we only have one IP address that is talking to the PLC and up to 32 slaves behind it. Less downtime because we can do drop-in replacement of slaves. You can also have your master pre-configured so that if the master fails, that's a drop-in replacement. The cost savings comes from the ability to use a lower cost PLC that would support fewer connections. There's no special hardware required, and there's no additional cost to use this feature. It's embedded in all of our firmware, and it does work with our multi-protocol Ethernet and works across PLC platforms as well. So I'm being told we get a couple of questions here, so why don't we just do a quick here.
Steve, first question is, by having multi-protocol Ethernet, how do you handle the multicast protocols?
So we can select let's see. So you can do that a number of ways. I mean, most of the protocols can be either selected to use multicast or unicast at the PLC. You could use a managed switch to narrow down that focus of multicast versus unicast. Our block will respond as it is requested to. So I don't believe we really have much of a setting in the block to deal with multicast or unicast.
Okay. Second question, do these blocks require an external 24-volt power? What's the current draw of the block and wire size of the power connector? Asking to determine voltage drop.
So the blocks, the TBN-L, each power bus, the V1 and V2, is capable of passing in 9 amps. The block can only handle a total of 11 amps between those two. As far as wire size, that's really dependent on the person running the cable. I mean, we have a variety of pre-molded cables and field wireables, so it can be wired with whatever gauge that you would like. The TBNS is 4 amps per V1 and V2 with a total of 5.5 amps combined between them. And the FEN20s or any of the IP20 products You're wiring to terminals, so you bring in whatever gauge wire is appropriate.
Okay, very good. That's it for now. On with the show.
Okay. So let's talk here very quick about field logic controller. This is also referred to as RG. RG is the programming environment. Again, this is something that is in the firmware of these blocks. If you choose to use it, it's there. There's no additional cost. If you choose not to use it, just don't enable it, and it's in the background and completely unused. So this gives us the ability to have logic and control actions take place in the block. One of the places where this is really handy is we see places that have a very remote item like a pumping station or maybe a drain tank. And we tend to lose communications to that area on a frequent basis. And like any I/O system, you can tell the block that, on a communications loss, turn all the outputs off. But there's no staging to that. It's just when the block detects the communications loss, all the outputs go off instantly. If you've got pumps pumping and a valve immediately downstream, turning the pump off and closing the valve simultaneously is probably not good. So by adding FLC to it, we can now stage that shutdown. So we could be passing through remote commands from a PLC until we lose communication. Then the RG program can take over and say, stop the pumps, wait 30 seconds, close the valves. So we are now working in a very staged and controlled method of shutdown rather than causing any water hammer or anything like that. The programming environment is simply using an HTML5 web browser. Right now, Chrome is our recommended web browser for this. And we can get scan times as low as 2 milliseconds. So RG has two environments. The first is our Flowchart environment. This is intended to be very, very basic, just to kind of get your feet wet in looking at RG. You get two timers and two counters. You cannot rename those. All of the inputs and all of the outputs are in the drop downs. So you have these little drop down arrows and you select the tag that you want. You do not get to name your tags. So we have our input conditions, we have operations, so and or nots, pass through if nothing's happening, and we have our action blocks. So we can count up on a condition, count down, timer on, timer off, set an output. So there's a lot of things we can do here discreetly, but it's not all that powerful. But we do have this convert to RG Pro button. So when we convert to RG Pro, the environment changes quite a bit. I now have a variable table. So I can create tags here. They can be words, 32-bit integers, bytes, strings, and they can even be arrays in this type. I have the ability to do aliased variables. So instead of having to use the long actual input name, I can make that input name something that's familiar to me. So pump one run, can be an aliased variable, and anywhere I turn that on, it's going to turn on the actual output by using an aliased variable. And we have function blocks. So function blocks become really handy. If I'm scaling an input, an analog input, I can set up a single function block to do that and run it like a function block and just pass parameters to it and get a scaled value back from it. We can also run these function blocks like subroutines, or we can run them as a task. You can see here, this one is selected to run as a task, so I don't even have to call it. It's going to automatically run every program cycle. And these function blocks have their own variables. One of the advantages to function blocks is it has allowed us to implement the concept of libraries. So we can create libraries that we distribute in our web page, and the user can import those library function blocks and gain access to some advanced code that's already pre-done. And one of those that we have distributed is a Ethernet IP master that can handle up to 8 slave devices. So it's really has changed RG, because now instead of just RG running on a block and controlling the block itself, I can now communicate and control up to 8 other devices over Ethernet IP. So it really makes it a lot more flexible and a lot more powerful. As far as the programming environment, you can see here that we have just regular statements. So you can have an assignment that says a value is equal to an expression, a calculation. We have comments, we have if statements, we have else if statements. We have calls to functions. So there's a lot of power that is available in the RG environment when we're in the RG Pro. Again, if then else, wait statements, for loops, while true loops. So a lot of things we can do in there that really brings us up to a PLC level in an IO block. So if you've got a machine or a small skid or something that is on the borderline of whether you want to just have it manually controlled by an operator or put some controls on it, this gets you a low-cost solution to get some controls. So IO Link is a topic. It's a great topic for cost reduction. If you're not familiar with IO Link, it is a point-to-point communication. It is considered a sensor bus as opposed to a field bus because it is point-to-point. And it is an IO Link master on the, we'll say on the PLC side, and an IO Link slave device on the sensor side. So we have a number of sensors that we produce. There are also a number of output devices. So solenoid manifolds, pressure regulators, that variable pressure regulators, stack lights. I've also seen used an electro positioner, so a little servo positioner that communicated via IO Link. And then we have IO slave hubs, like this little guy here in the bottom left. It is, as shown here, a 3-conductor connection. So it's plus and minus in our IO Link signal going out. Because it is a 24-volt serial signal, it is very robust. We don't have issues with noise. We don't require a shielded cable. So very easy to implement in the field as well. It does have a 20-meter limit. So 20 meters from our master to our slave is our limit. But again, if we're talking about Ethernet devices as our masters, these can be spread out 100 meters between IO Link masters. So we can cover a large area, even though we have that 20-meter limit. IO Link is typically referred to as communication to the last meter. So if you've heard the terms Industry 4.0 or Industrial Internet of Things, IO Link plays into that, because those two concepts, that's one concept with the same name, is all about getting more data back. So in the upper left here, we have our control system, our SCADAs, our DCSs, things like that, some of which may have IO Link masters directly associated with them. We also have field bus, which is pretty much what we've been talking about this morning, is field bus devices that are IO-Link masters. And this middle section here is IO-Link devices. And this is really key because these are the devices that communicate not only their process data, but their status, their health, whatever information the manufacturer makes available is available through message instructions back to the control system. So I will pick a few examples here. These devices here look like our typical proc sensors. So a lot of people would say, well, why would I use a proc sensor on IO-Link? It's a pretty simple device. Well, when we put a proc sensor on IO-Link, we get a couple of health indicators from it. It has a built-in thermistor, so we can watch the temperature, and it has a signal strength indicator. So I can tell when the signal strength is changing that my piece is not in the same location. So I can't really measure distance with it, but I know if I'm getting too close or too far away. If my temperature is getting hot, I know I've got a problem. At the same time, when there's no part present, with the digital signal, it's just off. You don't know if it's been disconnected, if it's not there, the wire's been cut. With IO-Link, I'm still communicating with it, so I still know it's there, but I know there's no part present. So I gain that advantage. If I look at something like a laser sensor, some of these laser sensors are very, very high resolution. But if you're using an analog signal, you're taking that high resolution signal and you're limiting it through a 16-bit D to A converter, where it's hitting at typically a 4 to 20 milliamp output. And as it goes across that cable back to the PLC, it's subjected to some noise, and then it goes through a 16-bit A to D converter. So we're limited to 16 bits, and we have some noise injected in. If I'm using an IO-Link, now I'm getting the process data serially, and there's no noise injected, and some of these devices have 27 bits of resolution that I get all 27 bits across the communications. So there's no loss of integrity in that data. We also have some process instrumentation. So if we have a process instrument that fails, normally when we have a process instrument, it requires somebody to know what was that instrument I took out span to, what was it the PLC span to, and I've got to set the instrument up and make sure it matches before I can get the process going again. If I have an IO-Link pressure transmitter fail, I replace it with a new IO-Link transmitter of the same product family, and it's just going to work because the PLC is going to have the ability to configure that device once it's plugged in, and there is oftentimes no spanning of the instrument. Most IO-Link devices are giving you full resolution across the full span, so there is no spanning of it. You plug it in, you're getting that full span data. And we often still have some conventional I/O points, discrete I/O points, and we can bring those into an IO-Link hub. The advantage to these hubs, they are typically a little bit less than half the cost of an equivalent 16-point Ethernet block. So if I had this as an Ethernet, our TB&L product family versus our slave hub, I'm going to save about half the price by putting one of these in. So it really works to cost reduction. So IO-Link port types. Class A ports are 3-wire, as we discussed earlier. Class B ports add 2 wires, so pin 2 and pin 5 by the IO-Link spec. The Class A port requires that we supply up to 200 milliamps to the end device. On the Class B port, pins 1, 3, and 4 are still 200 milliamps, but pins 2 and 5 need to be able to supply up to 2 amps. And that can be shut off via an e-stop because it is on the V2 power supply, not the V1 power supply. Some typical differences between Class A and Class B devices. So Class A is going to be things like the slave hubs, sensors, encoders, any type of advanced sensors, I'll say, pressure transmitters, stack lights, things that don't consume a lot of power. Class B, we do have Class B slave hubs. So solenoid manifolds. I can keep my communications active, but remove output power. The same with robotic grippers. So it allows me to have some functionality. There are also, so the electric positioner I talked about earlier, it was technically a Class A iLink device, but it had auxiliary power supply to it because it had a 120 volt power supply. So there are these combinations as well. So iLink, it's more than just a simple sensor interface. It allows me to reduce my I/O count because I put one iLink master out here. I can pick up an encoder that would have otherwise required a high-speed counter input. I can do RFID, which would have otherwise required an RFID interface. I've got discrete I/O points here. I've got an analog I/O point. So that would have forced me to 2 different blocks right there. We've got a valve manifold here. So most manifolds up to 16 valves, whether they're single or double acting, can be run from one iLink master port. And we have the things like grippers, which also typically use up a little bit more I/O points than just a single point, available with a single I/O port. So, we've reduced what could have been 4 or 5 or more I/O blocks into one iLink master block. So it helps us save money in that way. And then the other way that we save money is the use of just general purpose I/O. So these are non-IO-Link devices, all connected through IO-Link slave hubs. And if I'm using an 8-port IO-Link master block and I put 8 16-point IO-Link slave hubs, I can get up to 128 I/O points on one IO-Link master. So that is, if you have a high density of I/O points, because this cable here has a limit of 20 meters, but if you have that high density of I/O points, discrete general purpose I/O, IO-Link is going to save a lot of money because each one of these is a little bit less than half of its Ethernet equivalent. And finally, we have the concept of remote safety. So we have IP67 rated blocks with ProfiSafe and SIP safety. So we stop using multi-protocol Ethernet here. These are dedicated to ProfiSafe and ProfiNet on one block, SIP safety and Ethernet IP on the other. These are hybrid safety blocks because we have a combination of I/O on them. We have 2 digital safety inputs and 2 safety configurable in or out. We have 2 ports, which equals 4 I/O points of general purpose I/O. And then we have 2 IO-Link master ports. And how that looks with a functional safety sketch here. Each one of these is a unique functional safety input or output. And over here, we have functional safety outputs. So I can safely remove power from these general purpose discrete I/O points. That will not be SIL level 3, but depending on your application, everything involved, it could be used as a safety function. And the same down here for the bottom IO-Link port. So that is where the hybrid term comes in. We will be releasing very shortly our full safety blocks. So those will be 4 safe inputs and 4 configurable safe points. It will still be 2 blocks for SIP safe and Profi safe. And the sketch here, so the safety functions for the inputs, safety functions for the configurables. So, why the use of remote safety? Well, there's a lot of I/O points to a safety device, whether it's a light curtain or an e-stop button. So by having the blocks out there close to the point, we're saving a bunch of wiring coming back. These blocks do have the ability to have that safe logic in them. So they can be used really in 3 use cases. The first, where they're just passing the inputs to the PLC and any outputs are being passed from the PLC back. The second use case is there is no safety PLC. There's just the logic in the safety block. And then the third is a hybrid, where you could have a safety PLC, but have local action taking place in the block. And that hybrid becomes useful if you do your safety calculation and find out that the network update times are adding too much time to your safety mode, where the time between input action and actual stoppage. You can now have local action take place faster in the block, but still pass that information to the safety PLC so that it safely shuts down everything around it. So we do have that mixture of modes available. Finally, we have our safety shutoff relay box. So one of the issues with the safety blocks is that the output is an OSSD output. So if you wanted to remove power from a bunch of blocks like this, you still needed to put a little box out there with some relays. So we have embedded those relays in a box. There's 2 relays in series with force-guided contacts that meet all the safety requirements. So we have 24 volts coming in on V1 and V2. We have our safe output from our block going into the safe input on the safety shutoff box, and we have feedback going back to our general purpose input for increased SIL level. So if you don't have this, I think you're only SIL 1. On the output side, V1 is always powered. We're passing V1 through. V2 is shut off. And again, on all of our devices, V2 is our output power. And that can be on a general discrete IO block, or that can be our IO-Link master blocks. So any questions?
Steve, we do have one, it looks like here. Says, how does IO-Link compare to HART connected devices? Why would an engineer choose one or the other?
So HART is a very different technology because it's communicating over the 4 to 20 signal. So one of the differences right away is the distance limitation. On the IO-Link side, we have 20 meters. Analog signals can go hundreds, if not thousands of feet. So that right there is one point where it could be a breaking point. It's going to depend on your application, because if that little bit of noise and a little bit of ripple is a problem in your process application, then IO-Link can solve that, because HART isn't going to get rid of that noise on your 4 to 20 signal. We also have a little bit better access to parameters on an IO-Link device. Some of these IO-Link devices have dozens up to hundreds of parameters, and we can read any one of those we want. So every time that I see the connection is lost to an IO-Link device, when it's returned, I can query the part number of that device and see if it's the part I'm expecting. There's even an index number on every IO-Link device that is basically a user tag. It's called the application tag. So I can write to it and put a value in there so that I know, even if the same part number is there, but if the application tag is different, well, somebody changed that device out. So we have a little bit more functionality with IO Link than we do with HART. And we are going to be on Thursday, there's the follow-up to this presentation where we're going to dive a little bit deeper, actually a lot deeper into IO Link and how some of those parameters work and what we can do with them.
Cool. Those are all the questions that we have. Thank you again, Steve. We greatly appreciate this.
Sure, thank you. And if anybody thinks of any questions later, just reach out to your Gilson sales guy, and they'll get me involved, and we'll get your questions answered.
Of course. Yep. Thank you, Steve. And again, everybody, please join us on Thursday, same time for the follow-up session. Again, if you guys do want PDH credits, please email me at wr@gilsoneng.com, and we'll get you that documentation out to you. Thank you again, Steve. Have a good day.
Thanks, you too. Bye.